Hi everybody. I hope that you are all doing well this evening. I hope that everyone had a really nice rest for their winter break and just let yourselves recharge for this term. As you can see, the live streams are now going to be from 6 to 7 p.m. due to my new class schedule. They will be held every Thursday, and we're pretty consistent this time, so there won't be as many switch-ups as last term, which will be great. I will post the Google form like I did last time as well around the 30-minute mark from the hour, and then you can just fill in all of your information. I'll put it in a sheet so we can get you guys those points. Awesome, let's get started. So today we are going to be talking about evolutionary processes, and we're first going to do the review of chapter 23 and just fill in these definitions and get a better understanding of what we're looking at. So if evolution can be defined as a change in a gene, or more appropriately an allele frequencies, is it conversely true that a population not undergoing evolution should maintain a stable gene frequency from generation to generation? This was the question that Hardy-Weinberg answered independently. So all of the definitions we'll be dealing with are essential to understanding this theorem that Hardy-Weinberg came up with. And just a refresher, the Hardy-Weinberg Theorem states that genetic variation in a population will remain constant from one generation to the next in the absence of disrupting factors like alleles or mutation. And I know that that was a long description of it, but basically it's just that evolution is not happening. We're not getting mutated genes, no new things are popping up, things are in equilibrium. So A, population, an interbreeding group of individuals of the same species. Oh, and of course, if you have any questions, feel free to throw them in the chat and I will get to them as best as I can. B. Yeah, so the way that we mark attendance is I'm going to put a Google form in it at about 30 minutes. If you have to leave early, I can also do that at 6:20 instead. Just let me know how early you're leaving and then I can totally put it in before you have to go. So gene pool, all the alleles contained in the gametes of all the individuals in the population. Okay, cool. I will put it in there a little bit before that then. Genetic drift. Evolution, defined as a change in allele frequencies that occurs in small populations as a result of chance events. So this doesn't really happen on a large scale for genetic drift to have a huge impact. It's most impactful, I should say, on smaller groups. So 2, the Hardy-Weinberg theory. The Hardy-Weinberg theorem states that in a population that is not evolving, as we said previously, the allele frequencies and genotype frequencies remain constant from one generation to another. Assumptions. The assumptions required for the theorem to be true are listed in chapter 23 on these pages and are presented in shortened form. So, A, there are no random allele frequency changes. And I'm shortening frequencies to just freak. There are no random allele frequency changes that would affect the gene in question. B, there is no net migration of individuals into or out of the population. No one is leaving and nobody is migrating in. C, there is no net mutation. That is, the forward and backward mutation rates for the alleles are the same. For example, big A would mutate to little a just as frequently as little a would mutate to big A. Mating is at random for the trait / genes in question. And, oh, sorry, you guys can't see that. Awesome. And finally, there is no selection occurring whatsoever. Offspring from all possible matings for the trait / gene are equally likely to survive. Awesome. And that brings us to the end of our definitions, and now we're going to move more so into the math associated with the Hardy-Weinberg Theorem. So the Hardy-Weinberg Proof. Consider a gene that has only two alleles, big R dominant and little r recessive. The sum total of all R, big R, plus all little r alleles equals all the alleles at this gene locus, or 100% of all alleles for that gene. P is equal to the percentage or probability of all the R alleles in the population, and Q is the percentage or probability of all the little r. And I'll just highlight those here. Yeah, so that is the percentage of the probability of the R alleles in the population. So if all big R and all little r alleles equal 100% of alleles, then we can say down here P plus Q is equal to 1. The percent or probability of R in the population plus the percent or probability of little r is always going to equal 100% in this theorem. Conversely, using algebra, you can use one or the other. If you have a number associated with P, you can find Q. Because it's equal to 1, you can just do it algebraically, like here, where you do 1 minus P to get Q, or 1 minus Q to get P. And that becomes really, really helpful when things become a little bit more complex with the math. So note, frequencies are stated as percentages. For example, 50%, and their associated probabilities are stated as decimal fractions. Yeah. So assume that 50% of the alleles for fur color in a population of mice are big B, black, and 50% are little b, brown. The fur color gene is autosomal. So what percentage of the gametes in the females alone carries the B allele? So if we have 0.5 that are big B and 0.5 that are little b, and we don't have to worry about it being sex-linked or any of those rules. This is for autosomal cells. Then for females, this would just be 50%. And the little b would be the other half of that, so that would also be 50%. And since we're not concerned with sex and dealing with X chromosomes or Y chromosomes, then males for both alleles would have the same percentages. So E, given the preceding case and all the Hardy-Weinberg assumptions, calculate the probabilities of the 3 possible genotypes, big R, little r, and little r, occurring in all possible combination of eggs and sperm for the population. So in this case, what this would be is if this is P and this is P, that's P squared. So in this case, right here, we would get big R, little r, and PQ. And this would be the same for this box right here. We would be getting PQ when we multiply across. And this last box is just Q squared. And because all the offspring types present represent all possible genotypes, it follows that p squared plus 2pq plus q squared equals 1. And this is a super, super, super important, sorry, I need to get better about scrolling. This is a very, very, very important tool that you will definitely be using a bunch throughout the term. So make note of this, and we are going to take this and use it to solve some questions. And I'm putting the form right now for that one person who said they had to leave a little early. Awesome. So now we're moving on to part B. Use your understanding of the Hardy-Weinberg equilibrium proof and theorem to answer the following questions. According to the Hardy-Weinberg theorem, p plus q equals 1, and p squared plus 2pq plus q squared is equal to 1. And just a reminder, I'm just going to put an A, and I'm going to just label above what these kind of represent. So P would be the dominant, Q would be the recessive, P squared is dominant, and then 2PQ, all that good stuff right above. So what does each of these formulas mean, and how are the formulas derived? For P plus Q equal to 1, this is a summation of adding all the dominant and recessive alleles for one gene. Of dominant, sorry. And so this is just, this accounts for 100% of the alleles for that specific gene. And just make a note that this specifically assumes that the gene only has 2 alleles. So that's another, there's a lot of assumptions in Hardy-Weinberg you will need to keep track of, and that is another one that will help you solve these. For p squared plus 2pq plus q squared equal to 1, if you combine all the individuals that are homozygous dominant, heterozygous, and homozygous recessive for that gene, then you've counted and combined all the individuals in the population that carry that gene. That's what this equation represents. So it's the combination of all homozygous dominant and recessive and heterozygous individuals in the population. Two, assume a population is in a Hardy-Weinberg equilibrium for a given genetic autosomal trait. What proportion of individuals in the population is heterozygous for the gene if the frequency of the recessive allele is 1%? So the frequency of Q we said was 0.01 because it was 1%. And as we said earlier, we can find P as being 1 minus Q. And this ultimately equals 0.99 or 99%. And therefore, to get the frequency of the heterozygotes in the population, we are going to use 2pq and simply plug the values in that we got for q and p. P, we got 0.99, q, that's 0.01. And this is easier to do as fractions in my head, so I got, here, let me do this on my calculator with you guys so I can get numbers that are consistent. So the answer for this then would be 0.0099. Or simply 0.99%. And that is the frequency of heterozygotes. In this case, because it says the gene, if the frequency of the recessive allele, it is Q. But if they were to say the frequency of homozygous recessive people are 1%, then that would be Q squared. And that's a great question and can be hard to define when moving forward. So the next question actually deals with something where we're looking for Q squared, and differentiating has a lot to do with the language. Genetics is very specific, so if they're saying, you know, it's this allele, then you know that you're dealing with Q or you're dealing with P. If it says frequency of heterozygotes, you know that they're giving you something equivalent to 2pq. And all of that stuff can seem daunting, but I'm sure you guys would be excellent at it, and also it just takes a little practice, and I'm sure your professors will help you out too, and I'm also here as a source. So yeah, let's move on to 3 and deal with a question like that. About 1 child in every 2,500 is born with Phenylketonuria, an inability to metabolize amino acid phenylalanine. I read a lot, I don't speak these a lot, so it's always harder than I imagine. This is known to be a recessive autosomal trait. So A, if the population is in Hardy-Weinberg equilibrium, what is the frequency of phenylketonuria allele? So here it says 1 in every 2,500 is born with this disease, which we said was recessive. So 1 in 2,500 have, and I'm just going to do it in terms of R, little r, or Q squared. So this is an autosomal recessive disease. We're given Q squared, and we are asked to find the frequency of its allele. So all we would have to do here is square root this to get that Q is equal to 0.02 or 2%. So I hope that makes more sense. What proportion of the population constitutes carriers of the phenylketonuria allele? That is, what proportion is heterozygous? So we got Q. We solve for Q up here. We know that we can do something super easy to get P by just subtracting that value by 1. So P is equal to 1 minus Q, which is 1 minus 0.02. And P is equal to 0.98. We know that Q is equal to 0.02. And so to get heterozygous, we just plug it into 2pq. And we are given that the frequency of heterozygotes is equal to 0.0196 or 1.96%. Awesome. Okay. In purebred Holstein cattle, about 1 calf in 100 is spotted red rather than black. The trait is autosomal, and red is recessive to black. What is the frequency of red alleles in that population? This is super similar to the last one that we did. So it's saying that 1 in 100, autosomal, red is recessive, has this spotted red recessive gene expressed. So this is equal to Q squared. Alright, so we square root this guy. And we would get that that is equal to, Q is equal to 0.1 or 10%. B. What is the frequency of black homozygous cattle in the population? So it's not asking for the allele in this case. We're going to have to do a second step because it's asking for the homozygous cattle. Therefore, it's asking for P squared, the big A, not just A. So then P is equal to 1 minus Q. .9. We know our Q is equal to 0.1. Oh, we don't need that yet. Sorry, I thought we were doing heterozygotes again. So then we're just going to square this term to get P squared. So it's equal to 81% or 0.81. I did do all of this math. Oh yeah, for sure. And I know that I talk really fast too, so I'll definitely pause before every, when I complete every answer just to make sure. I'll definitely start doing that. Thank you. Also, these worksheets should be available through your biology class Canvas. So I'm not sure where, I know that people have different biology professors, so I'm not quite sure where they are for everybody. But I know that there should be a section through your Canvas modules that have like Learning Center live stream worksheets, and before the live stream they have the blank versions, and then they will post the key as well after. So I'm not sure, but I would check with your bio professor. If there's anything wrong with audio, technical, please let me know. I am still figuring things out, and I really appreciate your guys' feedback. It helps me just like be more consistent and more helpful to you guys. C. What is the frequency of black heterozygous cattle in the population? We have our P, we have our Q. We just have to plug it into 2PQ. Remember, we're not going to be using this value or this value. That's Q squared. I did do this math ahead of time, but I have my calculator out just to make sure that I'm getting the right answers. So I got 0.18 or 18%. Awesome. Okay, I'm going to move on to 5. There are only 2 parts to this. Assume that the probability of a sex-linked gene for color blindness is equal to 0.09, and the probability of the normal allele is 0.91. This means that the probability of X chromosomes carrying the color blindness allele is 0.09, and the probability of X chromosomes carrying the normal allele is 0.91. So now, awesome, I'm so happy you found that. That's great. Now we're moving a little bit deeper. So previously we solved a lot of questions discussing autosomal cells. So the inheritance of autosomal cells are going to be similar. Their mitosis creates 2 of the same cell, replication the same thing. So if it's an autosomal thing, we know that it's not sex-linked and it's uniform through females and males. It doesn't matter. It's going to affect them the same. Then we moved on to 2pq, p squared, q squared, solving for those when given only one value, and learning how to read those kinds of questions. And now we're moving on to dealing with extra rules, yay, for sex-linked. We're told that color blindness is sex-linked, and we know that it's going to affect males and females differently. Females have 2 X chromosomes, males only have 1. Females have more of an option to express the correct gene. For example, if they had a color blindness gene on one X chromosome, maybe that X chromosome is not the one expressed, and so they would appear phenotypically normal in sight. But for males, if they get it on their X chromosome, that is the only one that they have and the only one that is expressed, and so it's much more likely in males to express a recessive sex-linked sex-linked gene than it is females. Okay, so what is the probability of having a colorblind male? Because we only have one X chromosome, the probability is pretty much exactly what they told us. So the probability of having a colorblind male is equal to Q, which is equal to 0.09, or 9%. However, in question B, what is the probability of a colorblind female? Now we have to deal with 2 copies of the X chromosome. So they display the genotype for genes on the X. Okay, a colorblind female is homozygous recessive for the blindness allele. Then the frequency of the homozygous recessive genotype would be Q squared. So, I'm going to re-clarify. Sorry, I'm stumbling on my words. I haven't done this in a while, so I'm just kind of nervous, and I don't know why. But, the probability of a colorblind female, because they have to get, the little r and the other little r. It's not just one or the other as it is for males. You have to get Q squared instead of just Q, because, you're dealing with 2 X chromosomes. So that would be 0.09 squared, which is equal to 0.0081, which is a crazy, crazy, crazy smaller number than 9%. That's almost a 10% difference between the probability of males and females expressing this sex-linked recessive allele, which can just tell you about how prevalent and kind of cool and important it is, and how we see it in everyday life. Does anybody have any questions so far? I know that I'm going through these, so I just want to make sure that we're understanding. Quite the opposite. So females have a far lesser chance of getting the sex-linked genes than males because males have only one X chromosome and females have two. So if a female has a recessive allele for color blindness, but on her other X chromosome has the dominant allele that makes you see normally, then it won't be expressed. But for males, they only have one X chromosome. They have nothing to counteract it. So if they got the recessive allele for color blindness, it's going to be expressed no matter what. So males have a far greater chance, 9%, versus females who have 0.81% chance of expressing color blindness. Does that make sense? Yes, yeah, exactly. Yes, that's exactly right. Awesome, cool, great. So now we're gonna move on to number 6, or 6. This one says, the ear tuft allele in chickens is autosomal. So ear tuft allele is autosomal and produces feather skin projections near the ear on each side of the head. This gene is dominant and is lethal in the homozygous state. In other words, homozygous dominant embryos do not hatch from the egg. Assume that in a population of, I'm going to do a different color, of 6,000 chickens, 2,000 have no ear tufts, 4,000 have ear tufts. What are the frequencies of the normal versus ear tuft alleles in this population? Okay, let's do it. So the gene is lethal in a homozygous condition. Therefore, homozygotes that are produced don't hatch, they don't appear. So because we don't know how many eggs didn't hatch or how many of these contained homozygous tuft chickens, we need to calculate the allele frequency by assigning alleles to the existing population. So we don't know how many homozygous dominant. Those chickens don't even exist. They weren't viable. Yes. Having ear tufts means heterozygous. So because, so ear tuft would be like big A, little a. This is going to be sad, but dead is equal to big A, big A. And then no ear tuft is equal to little a, little a. So that's what we're dealing with here. It's good to like break it down. So the tricky part about this is because we have no idea about how many mice didn't even come to fruition. We're just dealing with these guys, and so we have to break these numbers up in terms of their alleles. So I'm going to make a little chart and hopefully break it down enough to where it'll make sense. Genetics is a lot about just like dumbing it down for yourself and working through it. So this is number of, let's change this. Sorry. Oh, shoot. That was a much bigger eraser than I thought it was going to be. Number of T or tufted alleles and number of T normal, little t alleles. That's why I erased the A's, is just because T's will probably be easier in this situation. And over here, it said up here that we have 4,000 chickens that have ear tufts. And we have 2,000 normal chickens. So tuft we know is big T, little t. 2,000 normal we know is little t, little t. We have to account for each allele separately. So we're dealing with this and this separately, as well as this and this when we're counting. So from the tuft chickens, the number of T would be 4,000, and the number of little t would also be 4,000, because there are 4,000 of this, and separately there's 4,000 of each. In normal, little t appears 2,000 here and 2,000 here, so we have to add those two. It actually appears 4,000 times. And now we're just going to total everything up. And so to get the frequencies of each of these, we're just going to divide the total of this by the complete number of alleles that we're researching. So 4,000 divided by 12,000, and that is equal to 0.33, or like somebody who got to super quick, which is awesome, got 1/3. Great job, you are correct. And for number of little t, 8,000 divided by 12,000, this is 0.66. And that is how I would approach this problem. I know it can be tricky, but just breaking it up for yourself. Oh yeah, for sure, sorry. So up top here, and I'll erase these so I can re-highlight, it says that we have a population of 6,000 chickens, that that 2,000 don't have ear tufts and 4,000 do. We determined that a chicken with a tuft ear were heterozygous because it said the dominant that having a tuft ear is a dominant allele, and having two of those dominant alleles would kill the offspring. So we don't know how many offspring had a homozygous dominant allele. We don't know how many had TT. So we're just going to have to determine the allele frequency based on the living organisms. So those with ear tufts with big T and little t, awesome. There were 4,000 of those. However, we have to deal with each allele completely separately. So because tuft means big T, little t, we have to separate out big T and little t independently. So if we see 4,000 tuft individuals, we know that they have this big T 4,000 times and this little t 4,000 times, because both of them combined as a heterozygous show up 4,000 times. Does that make sense so far? Yeah. So I don't know like how to explain this, but if you're thinking about, I just want to give you another analogy other than the problem itself. So if you're thinking about like a ball and a cube toy that are always like sold together, but they're independent things. Like one is a ball, one is a cube, and they're two toys. And if you got 4,000 of these, then you would have 4,000 circles and 4,000 cubes. One is 3D, I guess. One is 2D, I guess. 2D and a 3D toy. So that's why you have to account for t like 4,000 and little t for 4,000. And we did that for normal as well. The normal individuals have the frequency little t. Yes, exactly. Yeah, so we have to think about them. We have to think about them independently, and that's what we did for little t and little t for the normal allele. And so because there are 2,000 that we see, there are 2,000 of this little t and there are 2,000 of this little t. So does that make more sense? And so that's how we got 4,000 right here, because we have to add these two together. And because we saw 4,000 big T, 4,000 little t, 4,000 little t, then we just added. And that's how we got the frequencies. Okay, awesome. Cool. I'm so happy that makes sense. So just to complete the problem, I'm going to make a little chart of if these were in Hardy-Weinberg equilibrium, we would expect the following offspring in the next generation. The frequency of alleles in sperm be big T, where P is equal to 1/3 little t, where Q is equal to 2/3. And then the frequency of alleles in eggs is a little bit more complicated, where T is equal to this. And so all we do across the board, I actually want to move this down a little bit because we're going to multiply this across like so. With my fancy technology. And so we're just going to multiply and get those frequencies, where TT, big T is equal to 1/9. And this, oh shoot, that's why I didn't take it off shapes mode. Okay. So big T is equal to 1/9. Big T, little t, 2/9. So those are the frequencies. In the next generation, when you remove the homozygous lethals, the frequency of TT and TT genotypes would be equal. So this indicates that the assumption is incorrect. In other words, the population is not in Hardy-Weinberg equilibrium. So because it's saying the frequency of this and the frequency of this is just as likely, then the assumption of Hardy-Weinberg equilibrium is actually incorrect, because these guys don't exist. Alrighty. I think we just have a couple more questions. So I hope you guys are having a fun time. And yes, I believe so. Yes. Sorry, no, sorry. The frequency of little t, because we got the frequency of just the T allele itself, we have to multiply it by itself, so we get 4/9 as the frequency number. I am so sorry. I'm having a very hard time with my words today. I've been stumbling over them all day. All right. Number 7. How can one determine whether or not a population is in Hardy-Weinberg equilibrium? What factors need to be considered? Oh, then you're probably correct. Sorry, I was just using my calculator. I didn't mean to. I don't like it when people say no and I'm correct, so I apologize and I redact it. To determine whether or not a population is in Hardy-Weinberg equilibrium, you need to be able to calculate the numbers of individuals in the population that are homozygous versus heterozygous for the alleles. Okay. If you know the frequencies of each genotype, you can calculate the allele frequencies. And then, given those allele frequencies, you can calculate the genotype frequencies that would be expected if they were in the Hardy-Weinberg equilibrium. So, calculate genotype frequency and compare to population. A lot of times in genetics you'll see, or in the topic of genetics and biology, you'll see the kinds of questions that we just did where we're given this or that and just solving with Hardy-Weinberg equilibrium. If for these steps that I'm kind of laying out, why do we only do a Punnett square for 2 heterozygous and not 1? If you take this Punnett square and take away the math, all we're doing here is this, because we got the frequency right up here in this little 0.66 that is kind of hidden. We got the frequency of T, little t, and right in this 0.33 that's kind of hidden. We got the frequency of big T. So that's why the Punnett square looks like the way that it does. And all we're doing alongside this is like adding these numbers. So you can think of these as variables and, you know, plugging in 0.33 for T instead. So that's why it looks like that. Does that make sense? I can also like explain more too. Okay, cool. Awesome. Yeah, and thank you for asking that too, because I feel like that's a really good thing to bring up that really helped me actually. So when you can like dumbing questions down like this, and I know that this is pretty daunting. This is one of the more complex ones. That's why it was at the end. But I know it seems kind of daunting, but if you like break it down into simple terms like this, and you're like, okay, we have big T, little t, I always, like, even through the upper division genetics, I always just drew a simple Punnett square, and it was super helpful just organizing your stuff, and then you can plug things in where you need them, and it just keeps all your like numbers in order, and there's less error that can occur. So hopefully that's a tool that you can use. And so as I was saying, and how do we get 1 over 9 for big T, big T? Because we multiplied 1 over 3 by 1 over 3. And so that's how we got, this isn't helpful that I crossed it out like this. So frequency of big T is equal to 1 over 9. Yeah, of course. So sometimes you'll have a question like we've done, and you get the what would it be like in Hardy-Weinberg, and then maybe they have a different chart that's like, this is what this population is experiencing. Is it within Hardy-Weinberg? And so when you do your fun calculations, because you're an awesome biologist, you can be like, no, it is not. Things are changing. I can tell because these numbers don't match what the expected is. Or you can say, yes, it is. It follows the same path as this guy. So that's pretty much the factors that you need to determine it. And in real life, it's very difficult to do because if alleles show dominance, it's hard to distinguish homozygotes and heterozygotes. For example, I have brown eyes. My mom has brown eyes, but I know that my grandfather had green eyes. But you wouldn't be able to tell that she had a carrier, or she was a carrier of a different eye color, because she doesn't express it, I don't express it. So that's just something to take into account. So as a result, we just tend to look at the frequency of the homozygous recessive because it can give us a lot of clues. It's sometimes more rare, usually more rare, and so when you're working with that versus just the general public trying to get that information, it can be tougher that way. So yeah, we use recessive mostly. And this, if the recessive remains relatively constant from one generation, we use it as that evidence to assume the population is in equilibrium. So if blue eyes or green eyes are more recessive, then you would just measure how many people have that, because it's rarer to find, and that would kind of give you a clue if things are changing. Cool. And now we move on to the final question. Is it possible for a population's genotype frequencies to change from one generation to the next, but for its gene frequency or allele frequency to remain constant? Explain by providing an example. I have an example for you right now. So there are actually a number of ways that this can occur. One example that we're going to look at is assuming that inbreeding has occurred in two populations of mice. Inbreeding is something that increases homozygosity, decreases heterozygosity, but doesn't change the allele frequency because you're breeding within your own You know, you're inbreeding. You guys know. So this occurred in populations of mice, and let's say, well, let's label first. So inbreeding in mice. Exemple. In one population, the mice have become homozygous AA at a particular gene locus. I like drawing my genes on chromosomes. So we're saying in one population, this little chromosome has a big A and a big A. But in the other populations, the mice have become homozygous, little a, at that gene locus. So this is one population. The other hello? Uh-oh, hello? Technical difficulties. My pen stopped working. I'm going to use my finger. Bear with me. I'm so sorry. I charged it. Oh, jeez. I'm so sorry. Oh, there we go. Okay. I'll do this fast. Okay, so that's the other gene locus. Equal numbers of little a, and big A mice happen to migrate to a new habitat. So there are equal numbers of both of these. The frequency of the A allele is equal to 0.5, and the frequency of the little a allele is equal to 0.5. Yes, so the gene locus, it's like a specific gene in a chromosome. So they're saying, like, this is one part of the chromosome, and then it's been switched to this. So this little a isn't found in other place. That is what replaces that specific gene and causes that difference. So we can also see, like, heterozygotes like this. I just like displaying it that way because the chromosomes help me, like, visualize where it's at. And so to prove this, we're just going to list all of the population, all the possible combinations of matings in the population, where we have AA females and little a females. AA males, and this is just a simple Punnett square. Don't get too lost in the weeds. So this can have all AA offspring. This will have all AA offspring. This will have AA, big A, and little a offspring. And this guy will have all AA. So each of these matings would occur with equal probability, and therefore each of the offspring types would occur with, So equal probability, therefore each of the offspring types should occur with equal probability. As a result, 1/4, I'll do this in a different color, 1/4 of the population, that's a terrible color, it's just too bright. Alright, 1/4, that's much pleasing, more pleasing to my eyes, of the offspring is a big A, because these two are 1/4, it's actually going to be 1/2, and this is 1/4. So in this case, the frequency has actually remained the exact same than it did before, because we have complete equal we have 50% of the A and we have 50% of the little a as well in this case. Alrighty. Cool. Oh, 7 on the dot. That is awesome. Well, it's 7 on the dot on my end. I know that, why is this a Punnett square for AA over A? Little a? Yeah. It is. So it's saying just like, it's breaking these up into its components, and I just simplified it for you here. So if we have AA females, AA males, all the offspring is going to be AA. If we have AA male, but AA female, all of them are going to look like this. I don't know why this did this. Sorry, that's confusing. Yeah, and then with little a, all of them will be little a. So, yeah, I just break them up into little parts, little Punnett squares, and helps me solve. So, yeah, cool. Are there any other questions? I'm going to put the form, I put the form in much earlier in the chat. And yes, yeah, it's just to account for all the different possibilities, and I just simplified it in the bigger table. I did put it in the chat a lot earlier, so sorry that I didn't do it again. I'm usually good about putting it in a couple of times, but if you're here for extra credit, please put your information in this Google form so I can get you on the Excel. Yeah, are there any other questions? If you, that's totally fine. Here, I can, I'll go into my form settings. Okay, so I have now turned off the setting that says, limit to 1 response. So you can just put your information in again, and then put your bio instructor's name. And so I'll know you because, you know, your email and your name will be the same, and then I can just do the right one. But can you put like dash correct one on the second one just so I know for sure? And yes, that is exactly what you would do. You would just multiply them for the certain genotype frequencies, and that's what we got here when we did this. Next time you see me, I will have a charged Apple Pen. But if there aren't any other questions, then I will see you guys next week, and I hope you have a restful evening. Thank you for bearing with me. I know this is kind of late, so I really appreciate you guys showing up and participating. Thank you. Have a great day.